Hello, in this video lecture we are going to learn the geometrical aspect of eigenvalues and eigenvector. So we'll take an example, and by means of that example we'll learn the how geometrically we can understand the meaning of eigenvalue and eigenvector. So let's take a 2 cross 2 square matrix which has entries 2, 1, 0, 3. We first wish to have its eigenvalues and eigenvectors. So let's just quickly calculate the eigenvalues and eigenvectors by solving the characteristic equation determinant A minus alpha I equals to 0. So when you put the matrix A here, so it is going to be determinant 2 minus alpha 1 0 3 minus alpha equals to 0. Once we solve this determinant, it is going to give us 2 minus alpha times 3 minus alpha equals to 0. That means alpha has the value 2 and 3, and these 2 and 3 are the eigenvalues of this matrix A. So we listed our eigenvalues, which are 2 and 3. So now we'll have the corresponding eigenvector with respect to the eigenvalue 2. So let's choose the value of alpha as 2, and to have the value of capital X here, we'll put A minus alpha I x equals to 0 and alpha as 2 here. And you see here it's a homogeneous system of linear equation. So by putting the value of A and solving this A minus 2i, we are going to get the coefficient matrix 0 1 0 1 times eigenvectors x1 x2 equals to 0 0. So from here we can have the values of x1 x2 and they are going to be our eigenvectors. So it's a very trivial system of linear equation, and we can have quickly the solution. It has x equals to c and x2 equals to 0. So we got our eigenvector with respect to the eigenvalue 2, which is x equals to c comma 0, and we can take c out of it and we can see a particular eigenvector for this eigenvalue 2. So any scalar multiple of 1 comma 0 is going to be an eigenvector of this matrix. Few of the examples are 1 comma 0, 2 comma 0, 3 comma 0, and so on. So here you can easily observe that eigenvectors are not unique. Once I solved a system of linear equation of eigenvalue problem, then all possible scalar multiples of that particular eigenvector are also going to be the eigenvector of the same matrix for the same eigenvalue. So let's try to understand. We have drawn a Cartesian coordinate system, and here what we'll try to learn what would be the impact of this chosen matrix A, which is here 2 1 0 3, if I multiply with any point which is lying in this Cartesian coordinate system. So surprisingly, there exists a class of line. It may be a 1 line or 2 line depending on the number of eigenvectors, where if you multiply this matrix A to those points in a vector multiplication, say matrix multiplication, it is going to map the image onto the same line. We can understand here with this example, we have multiplied A with 1 comma 0 and we got 2 comma 0. So what is happening, this 1 comma 0 is mapped on 2 comma 0, and whatever point you choose on this x-axis, which is actually the collection of all eigenvectors in our case, it is going to map onto itself. It is not going to beyond this line. So this is one of the fundamental and geometrical aspect of eigenvalues and eigenvectors. So let's take another example where we have a matrix B, where we have a matrix B whose one of the this matrix B is also 2 cross 2, whose one of the eigenvalue is 2 and the eigenvector is say 1 comma 1. Now we wanted to understand what these 2 and 1 comma 1 mean here. 1 comma 1 is an eigenvector, so any scalar multiple of this 1 comma 1 is going to be again an eigenvector. So the all possible scalar multiplication of 1 comma 1, they will provide us this y equals to x line. So now whatever point you choose on this line and multiply with the matrix B the way we are doing, it is always going to map onto the same line.